Alright, our last two projectile motion example problems. These will be projectiles that are getting thrown at an angle, so there is like maybe one extra step you have to do. First example, a football is kicked with an initial speed of 12 meters per second at an angle of 40 degrees from the horizontal. How far will the football go? So here's what we've got. Here's the flat ground. We've got the football. It's getting kicked like this, 12 meters per second, and the angle here is 40 degrees. We want to know how far does it go. Okay, that would be x, in other words. So we're going to do the same thing we always do, split everything up into x's and y's. Let's do x first. The initial position, we might as well, let's do an axis. Makes most sense to do this, x, y. X naught makes sense to say it's 0. X is what we're looking for. The initial velocity in the x direction, you might be like, well, we don't know that, okay? We were only given the initial velocity. Well, it is true. We do know the initial velocity is 12 meters per second, and we know that the angle here is 40 degrees, but we can figure out the initial velocity in the x direction just based on that. Remember, if you have a vector like this, 12 meters per second, and you know that, and this is totally not to scale, that's 40 degrees in the x direction, you can find the x and y components very easily. I'm going to resketch this because that was terrible. 12 meters per second. You have the x and y components here if you use trig. If you want to know the initial velocity in the x direction, all you have to do is realize that's the adjacent side. You already know the hypotenuse, and the cosine of 40 equals adjacent over hypotenuse. Cosine of 40 equals v naught x over v naught, which would be 12 in this case. Rearrange that, and you see that to find the x component, you take the overall vector, which is 12 meters per second, and you multiply by the cosine of 40 degrees. That turns out to be, let's do it the other way, 40 cosine 12, 9.19 meters per second. As far as the final speed in the x direction, we know that since there is no acceleration in the x direction, it's 0 meters per second squared, the final velocity in the x direction should be the exact same thing, 9.19 meters per second. There's all your x variables. The only one we don't know is x. We don't know the time. Let's focus on the y variables now. And I realize I'm not making this very pretty. The initial velocity, the initial position in the y direction is 0. There are some more variables that you might want to consider when you're dealing with projectiles thrown at an angle. For instance, perhaps we want to know what the maximum height is. I just call it y top. What is the position when it's at the top of its arc? We don't know that. However, we do know the final y position. We know that that should be 0 because it comes back to the ground. The initial y velocity might be another thing you say, well, hey, we don't know that, but we can use trig to figure that out. Just like the initial x velocity was the initial velocity times the cosine of the angle it gets launched at, the initial y velocity is simply the initial velocity of 12 meters per second multiplied by the sine of the angle it gets launched at, because this side, this y component, is opposite the angle that we know. Opposite over hypotenuse is sine, so sine of 40 equals v naught y over v naught, which is 12. Rearrange and you get 12 times the sine of 40. 12 times the sine of 40 is 7.71 meters per second. We might want to know the velocity in the y direction at the top. And if you think about it, if you remember, at the top of any of an object's path in projectile motion, it has stopped going up, but it hasn't started going down yet. Okay, so the upward velocity is gone, but there yet, as of yet, isn't any downward velocity. What does that mean? That means that the velocity at the very top in the y direction must be 0. And a neat little trick, the final velocity in the y direction, the velocity it has in the y direction just before it hits the ground, is just the negative of the initial velocity in the y direction. And that is true as long as it lands at the same height. So that should be negative 7.71 meters per second. And, as usual, the acceleration in the y direction, since we said up is positive, that should be negative 10 meters per second squared. Okay, so this is fairly standard. All we have done so far that's different is we took an initial velocity that was at an angle, not necessarily horizontal or vertical, and we broke it up into components. The only other thing we did is we allowed for maybe we want to know how fast it's moving at the top, maybe we want to know what the position is at the top. Everything else that we've done is exactly the same. So we want to know how far the football goes. The last couple times we've done that, we've had success using this equation. X equals x naught plus v naught x t plus 1/2 ax t squared. Okay, the initial position in the x direction is 0. The acceleration in the x direction is 0. I again am left with x equals v naught x times t. I have v naught x, 9.19. We just don't know the time. So again, we're left to use the y direction to find the time. And that's totally possible here. You can do this in a number of ways. Here's how I'm going to do it. I'm going to use what you guys learned last year as the fiat equation, but I'm going to make a few changes to it. I'm going to write Vy top equals V naught y plus Ay t. In other words, I'm going to find the time for the object to go from having this velocity, the initial velocity in the y direction, 7.71 meters per second, to the velocity when it's at the peak, which is 0. Okay? It doesn't matter that this isn't the actual, this is the spot for usually the final velocity. It doesn't matter that it's not the actual final velocity. All that matters is it does come after this time. It doesn't have to be the actual final velocity, and I'll show you why in a second. So we get 0 equals 7.71 meters per second plus a negative 10 meters per second squared times t. I bring that to the other side. I divide 7.71 times, oops, my bad. So let's see, 740. I divide that by 10, and I get that the time that it takes for the football to go from having this speed to having 0 speed, this velocity to 0 velocity, is 0.771 seconds. Now, think about this for a second, okay? That is just the time to go from here to here. But we want to know how far the football goes in the total overall in its motion, not how far it goes until it hits the peak of its motion. We want to know the total x distance it travels. So what do we have to do with this time? We have to multiply it by 2. And we get that the actual total time is 1.54 approximately seconds. Now, that's what goes here. That's what we need to fill in here. So now that we know the initial speed velocity in the x direction of 9.19 meters per second times 1.54 seconds, we can find that the position in the x direction, the distance, the displacement it has in the x direction, is 14.18 meters over this time. And again, the coolest thing about kinematics is that you can literally try this. You can kick a football at an initial velocity of 12 meters per second at an angle of 40 degrees, and it should travel about 14 meters. This is something you can literally try. You can practice this and try it out. Is it going to be a little bit different due to things like air resistance? Absolutely. But is it going to be about 14 meters? Yes. It should be just about 14 meters. It shouldn't be anything wildly different. The last example that I have for you is based on, number one, I'm the volleyball coach, so I have to have a volleyball question in there. It's also based on a question that I answered that I had to solve back in college. And the one in college was a little bit more complex than this one, but it was still just as interesting. It was a very hard question. I remember it took probably 2.5, 3 hours for me to kind of work it out on my own over a long period of time, but it was very, very interesting, and I know you'll call me a nerd. I had a lot of fun solving it. It was a very interesting problem. A volleyball player serving the ball has to make sure that the ball goes over the net. It's 9 meters from the back line of the court from where they serve to the net. The net is 2.43 meters tall. If a player serves the ball from a height of 2 meters with a speed of 13 meters per second at an angle of 30 degrees above the horizontal, determine whether the ball goes above or below the net and by how much. So here's our person. Let's draw a picture first. Here's our person, here's the ball. That ball is getting served from a height of 2 meters. The ball has to travel 9 meters to get to the net, which is 2.43 meters tall. Player serving the ball at a speed of 13 meters per second at an angle of 30 degrees. We want to know, where does the ball go? Does it hit the net? Does it go over the net? Does it just hit exactly at the very top of the net? And whether it goes above or below the net, by how much. Okay, so this, it sounds like a really complex problem, but it's very similar to the rest of these problems that you've done so far. We're going to write down what we know. We're going to write down what we're looking for. We're going to use kinematics equations to solve. We know that there is no acceleration in the x direction once the ball is served, so that's 0. We know that the initial position, we might as well say, is 0 meters in the x direction. We just want to know where the ball is at in terms of height when it gets to the net. So that means the final position, we don't even care if it goes, if it lands in. We just want to know, how high is that ball when it gets to the net? Is it going above or below the net? So the final position in the x direction is 9 meters. We don't quite know yet the initial velocity in the x direction, but we do know the initial velocity overall is 13 meters per second. We know this angle is, let's see, what is it, 30 degrees. We don't know the time. So I can find the initial velocity in the x direction because I know that I can take this vector given the magnitude of the vector and the angle that it's at, and find the x and y components. So the v naught x is going to be v naught times cosine of theta, which is 13 meters per second times cosine of 30 degrees. And that looks like 11.26 meters per second. And we know, since there's no acceleration, the final x velocity has to be the same as the initial x velocity, so that's the same number. As for the y's, y naught is, it's actually not 0, it's 2 meters, since the ball starts 2 meters above the ground. I'm just going to put the final velocity, or the final position, again, is the position when it gets to, when it has moved 9 meters. So that's what we're looking for here, okay? I'm just going to put a 9 there so we remember that that's what we're looking for. How high up is it when it's traveled 9 meters? The initial velocity of the ball would be, again, the initial velocity times sine of theta. If that's a little confusing, make sure you go back and review the vectors notes. And let's see, that would be 13 meters per second times sine of 30. Sine of 30 is a half, times 13 is 6.5 meters per second. Let's see here. Now we don't know, okay, so maybe we want to know the speed of the ball, the vertical velocity of the ball when it gets to that net, when it gets to the net. We don't know, that could be the peak, it could be before the peak, could be after the peak. It's kind of unclear right now, but you know, maybe that's something we want to know. And then the acceleration, oh, we didn't put our axis. Let's do our standard axis. Negative 10 meters per second squared. Okay. So, what we really need to know is how high up the ball is at a certain, when the ball gets to here. So, my idea is, why don't we just see if we can solve for that right now? Why don't we try out this equation? Y equals y naught plus v naught y t plus 1/2 ay t squared. I know this is going to be 2. I know the initial speed in the y direction. I don't know the time. I know the acceleration. Again, I don't know the time. So this is a case where I'm looking for y. If I just knew the time, this would be useful. And it turns out that there is a really easy way to find the time, because I know the distance that it travels in the x direction, or I know the displacement in the x direction, and I know the initial velocity in the x direction as well. And since it's the x direction, I know that the velocity doesn't change, so I actually know that it's moving at a constant velocity in the x direction, which means that x, vx, the speed in the velocity in the x direction, must be equal to x minus x naught over t, the change in position over the time that it takes. We're solving for the time. I know that the velocity is 11.26 meters per second. I know it starts at x equals 0. I know the final position is 9 meters times t. If I cross multiply, I get 11.26. T equals 9. I divide 9 by 11.26 to get rid of it, I get that t is 0.8 seconds. Just under 0.8 seconds, so we'll round it up to 0.8. Now I'm clear to plug in, and I can find the position of the ball, the vertical position of the ball, at that time. Has an initial height of 2 meters, or initial y position of 2 meters, plus 6.5 meters per second multiplied by 0.8 seconds, plus 1/2 negative 10 meters per second squared times 0.8 seconds squared. Okay, so this is going to be y equals 2 plus 5.2 plus, let's see, that's going to be negative 5 times 0.8 times 0.8 minus, 3.2. Okay, so I do 2 plus 5.2 minus 3.2, and I get y equals 4 meters. Now that's not the answer. I didn't want to know just how high the ball is going to be after it's traveled 9 meters horizontally. I want to know, does it go over or below the net? Well, the net has a height of 2.43 meters. The ball is at 4 meters. It's clearly above the net. If I subtract off the 2.43 meters, I see that the ball is 1.57 meters above the net when it passes it. Okay, so another interesting projectile motion example. As you notice, it's all about writing down what you know and then looking at that and trying to fit equations to that. Okay, in this case, with projectiles thrown in an angle, it's really no different from the other ones we did in the other video. The only thing is that in order to get the initial x and initial y velocities, you have to use trig. That's really the only difference here. Okay, other than a couple minor things about that just come with practice. That's really the only difference. You split things up into x's and y's, then you go from there. Notice that after I split up the initial velocity into x and y components, I never use the initial velocity again. That's a mistake a lot of people make. So that's it for projectiles, and that's it for projectile motion. That's it for the kinematics notes. I'll be back to talk more about forces later on. If you have any questions, please feel free to contact me and be happy to go over anything with you. Good luck, and I'll talk to you later.